Greetings everyone, we are Team Outliers 2. Welcome to our prototype demo video for OrbitIQ. OrbitIQ is a focused solution designed for ISRO to predict time-varying patterns of the error buildup between uploaded and modeled values of both satellite clock and ephemeris parameters of navigation satellites. It integrates advanced ML architectures with physics-based modeling to estimate and forecast deviations between broadcast GNSS values and ICD modeled parameters, enabling precise orbit and clock error predictions for future epochs. The platform supports flexible data uploads. Users can input datasets of varying durations for different satellites. We can also configure validity windows ranging from 15 minutes to 24 hours, aligning with ISRO's accuracy requirements. Our team is fully sure, confident, and committed in delivering the most accurate and reliable error prediction system for ISRO's needs. We will ensure and work hard to achieve the highest precision as required by ISRO. Now let's move to the dashboard. Here I have the option to upload my dataset file. Now it shows us the total number of satellites, the total data points, and the last data stamp. It also has a 3D visualization model. Let's go to data analysis page. Here I can choose which dataset to analyze, and it also has the option to select satellite, so it is capable to integrate multiple satellites in one software, and we can choose which satellite we want to evaluate. Now we can choose a time series parameter. For example, let's choose X error. I have chosen the time range from 1st September to 7th September. It has now plotted the X error versus UTC time graph here. I can configure the timestamp range. This is the statistics panel. Here, skewness measures the asymmetry of a data distribution, indicating whether its values are clustered more on one side of the mean than the other. Skewness has a significant impact on machine learning model performance. Kurtosis measures the tailedness or the presence of outliers in a dataset's distribution. A high kurtosis suggests heavy tails and potential outliers, while a low kurtosis indicates lighter tails. This is the correlation heat map. Correlation heat map can be used to visualize the strength and direction of the relationship between multiple variables. Heat maps make it easy to spot strong relationships. Now, let's go to 3D visualization. Here we can input the satellite and get the actual path versus error path visualization. Here points are color coded and sized by total error magnitude. The orbital paths are simulated. For example, it is showing for satellite 1 the XYZ coordinates. As this is just the prototype stage, we have used Streamlit here. But for the grand finale, with guidance from our mentor, we are open to integrate JavaScript so that we can enable more realistic 3D Earth modeling. Now let's make predictions. Here I can choose satellite type and the prediction horizon. For example, let's choose it to be 1 hour. Now I will choose models for comparison. transformer, and GAN. I can choose satellite for prediction and the time range for training data. Now, let's run comparison. Here on the left side, I can also choose the sequence length, transformer blocks, hidden units, etc. It has now output these results. RMSE refers to root mean squared error. That is a widely used metric to evaluate the performance of regression models. Mean absolute error is calculated by taking the average of the absolute differences between the predicted values and actual values. R square score, also called as coefficient of determination, it is a statistical measure that indicates proportion of variance in the dependent variables that is predictable from the independent variables. R square of 1 means that the model perfectly predicts the outcome. Shapiro-Wilk p-value determines whether a dataset is likely to have come from a normal distribution. If the p-value is greater than 0.05, you fail to reject the null hypothesis and can assume that the data is normal. High p-value means that data does not significantly deviate from a normal distribution. KS test refers to Kolmogorov-Smirnov test, that is a non-parametric statistical test used to determine if a sample comes from a specific distribution or if two samples come from the same distribution. It works by finding the maximum difference between the empirical cumulative distribution functions of the samples and the theoretical cumulative distribution functions. This is the graph. This blue line shows actual error and the rest are predicted errors by machine learning models such as LSTM, GRU, transformer and GAN. Here we have the QQ plot for normality check and the residual distribution histogram. We can even zoom in here. Now I can download the results as a full prediction data in the format of a CSV or Excel file. So this is the Excel file and here we can see the predicted errors values shown by various ML models. For example, for 1st September at 8 o'clock the actual value was minus 3.6 and predicted by LSTM, GRU, transformer and GAN are as follows. I can also use these values and use the integrated Excel tools to make charts. Like this. So, as promised that with more development time, we would make the UI with advanced functionalities and richer insights. We have done something like this. Now, for the grand finale, we will now focus on making our ML techniques more advanced to achieve state-of-the-art accuracy. Thank you.